Started. So as a reminder, today is going to be pretty much one of the last days of what I would sort of call synthetic organic chemistry with respect to reaction synthesis. And then moving forward, we're going to end up translating or transitioning into more applied aspects. Guys, quiet it down. Guys, class has started. Not chit-chat time. So just to sort of finish up from last class, one of the things that we started discussing was sort of alylation chemistry, right? Where if we had situations where we had some type of an allyl group, like let's say, for example, an allyl acetate, right? And as we sort of spoke, if you take this molecule and you treat it with, say, for example, palladium catalyst, right? What's going to happen, right, is we're going to insert into that bond. Right, and in this case, what we can have is a palladium allyl species, and like we said, you can effectively migrate this palladium source to either side of this. Right, and if we have a system like this, right, depending on how you want to think of the mechanism, one of these could then react with a nucleophile, and as we sort of discussed the potential products that could form, again, you could imagine 1,4 type addition or 1,2 type addition. I guess it would be 1,3, so we could either attack here or we could attack here. Same way over here or over here. But at the end of the day, what's sort of important, it doesn't really matter which one of those you draw. But perhaps from a sort of thinking about and rationalizing which one would form, perhaps 1, 2 might be a little bit more logical, because when you take this molecule and you treat it with a nucleophile, as we sort of discussed, what your intuition might tell you based upon thermodynamics, right, is that the molecule that has more substituted alkene might form, right? And so we could perhaps draw some parallels here to aspects such as Zaitsev's rule and elimination, just speaking to the strength of having, or the stabilization factor of having more substitution on that alkene. And if you think about a sort of 1,2-like displacement where we attack directly on that carbon, you know, at that point you might start to think about it as being more sterically driven as well. So for the sake of this course, you know, certainly, you know, I think the book says that, I took a look to see what the book would say, and I think the book said that it always goes this way. I'm not sure that's entirely true. I think you can imagine depending upon systems, and that's one of the reasons why I think it's got to be careful in organic chemistry to say it will always do this or it will always do that. But for the sake of this course, given that you can certainly draw the parallel to, say, for example, Zaitsev's rule, recognize that sort of more substituted alkene would form. What that basically means, right, is that you can imagine multiple substrates that via nucleophilic alylation chemistry would likely lead to the same products, right? So if you had a situation where, say, for example, your acetate was over here, right, in these instances, right, you're going to insert. In that case, what you're going to start with is this one, which would then again undergo that sort of 1,3 migration, and in principle, if you start with this one or this one in the presence of a nucleophile, you're going to get the same product. Again, given the fact that you have this migratory sort of isomerization, if you want to call it that, process. I thought I would sort of just show you guys a really what I thought was kind of neat example in the literature that I was sort of exposed to when I was in graduate school. It involves this reaction, involves, I think, a pretty interesting modification to this reaction. You guys know about, certainly at this point, we've discussed the importance of chirality, right? And when you have molecules that are, say, for example, single isomer, stereoisomer, or if you have molecules that are mixtures. Certainly there's been examples over time, right, where drug racemates, maybe, for example, one isomer of that has different properties than, say, for example, the other isomer. So having molecules that are single isomers, since we are chiral, especially in therapeutics, is very important. Now, it turns out there's a reaction, a molecule that I actually, one of the reasons why I knew about this well when I was a graduate student is because I worked on this class of molecules. This is a molecule called a gamma hydroxybutanolide. We actually worked with them a little bit in our studies. Actually, this was one of the questions, for example, on the exam involved the mean displacement of that, and you guys, most of you had mechanisms that weren't what I meant. We were actually simplified it dramatically. But anyways, that's not the important point here. The important point is that in these molecules, right, you have a stereocenter in this molecule. And so it's virtually impossible to make this molecule as a single enantiomer. And the reason for that is that you're going to rapidly undergo chimerization of this molecule through sort of ring openings, right? So imagine you protonate that, and then subsequently ring closing, right? So again, with proton transfer is intermediate in those steps. So the sort of fact that you open and close that, when this is a chiral, right? However, when it adds in, you generate a new stereogenic center. And so the way that you generally make these molecules, and one of the ways that you can make them very quickly, is, say, for example, to start with furan, right? So furan is very inexpensive. You could formally do, this is kind of neat, I guess we can take this opportunity to revisit Diels-Alder chemistry and show you guys a little bit something interesting. And that's that if you take oxygen and do I'll just sort of keep it simple, you actually do a Diels-Alder reaction with oxygen, okay? So how you do that, well, you have these sensitizers that make oxygen what we would call sort of singlet state. Normally oxygen actually exists as a diradical. I don't know if you guys are familiar with that, but if you excite it, you can actually bring it to this sort of double bond character. It's highly reactive. It does Diels-Alder chemistry. And then in the presence of, say, for example, a base, what can happen is you can open this molecule. So very cheap, very quickly, using furan, which is cheap, and using oxygen, right, and just a little bit of a photosynthesized light, you can actually generate these molecules really quickly. So they're valuable building blocks, and the thing is that this sort of 5-membered lactone structure is fairly well represented, specifically in, say, for example, natural products and bioactive natural products. And so you could imagine how a molecule like this might serve as an interesting starting material for a lot of different applications. Yeah. It's somewhere in the vicinity of a carboxylic acid, a little bit lower. Sorry, a little bit higher. So it's a little bit less acidic than a carboxylic acid, but in that ballpark. Again, because you can sort of see the resonance form of it. Right, because really this is just a tautomeric form of this. So it's tautomeric form is carboxylic acid. Anyway. How does what work? Be deprotonated? It just depends on the pH of the solution. Right, so certainly depending upon what the pH is, if you're just in an aqueous environment, or sorry, if you're just in an organic environment and there's no bases around, nothing's going to happen, right? So, all right, anyways, so you can imagine a molecule like this could have some sort of interesting abilities in terms of building blocks, but certainly the fact that you have the starting material that's sort of racemic can certainly cause issues associated with that. And so a really nice example of a Lillich alkylation that I saw in the literature that I thought was pretty nice came out of Barry Trost's group, and his graduate student who's now a professor at Berkeley in Haas. And in this chemistry, what they did was they took these molecules that I just showed there, such as that, and they, again, we'll draw the squiggle, sometimes you'll see this, and they had sort of a Bach protecting group, but again, we can think about that as a sort of an acetate. And if you look at this group here, right, what we have is a molecule which is formally allylic in nature, right? So our allyl group, a little bit different, right, because it's got the carbonyl flanking it, but built within there is that allyl ester group, right? And so as it turns out, right, if you could imagine if you took this molecule and you treated it with a palladium source, palladium 0, for example, what's going to happen, right, is you're going to get that insertion, right, into that bond. And once you get this, you have in essence this new palladium, I'll just say ligand over here, because as we'll sort of get to, they do this in the presence of chiral ligands, right? So what ends up happening is you get to an intermediate that looks something like this, right? It's a single enantiomer, right? But what can happen is that now, as we sort of said before, this can isomerize very quickly based upon the mechanism that we laid out previously, right? And so based upon the pi-allyl system, what can happen is you can imagine a system where you have two enantiomers, right? But these aren't enantiomers at this point if your ligand is now chiral, right? If you have, say, for example, a ligand, and that ligand is a specific chirality, right? The new molecules that you're going to make will have a set stereocenter over here on both of them, but they'll have different stereocenters over here, right? So those molecules will in essence be diastereomers, okay? And now that you have diastereomers, you can imagine that there could be some energetic preference, say for example, for one diastereomer over the other, right? Based upon the ligand, right? Diastereomers, as we know, can sometimes have energetic differences. Enantiomers cannot, right? So now you give them the potential ability to have different energetic parameters, perhaps favoring one over the other, and if suddenly now this one is favored, then what's going to happen is only this one's going to react. This is going to completely go to this enantiomer, right? And if you have a nucleophile, in this case it was aryl alcohols, you can now get to single enantiomeric cross. Yeah.
What is the element production in the when you have that ligand?
What is the ligand?
Yeah. What next? Like the next to the isolate.
That's a plus ligand.
No, the next to the terpene. What is that?
Oh, this squiggle line?
No.
That's the terbutyl.
Yeah, terpene next to that.
That's an oxygen.
Oh, that's not.
Yeah, so that's a carbonate. That's a Bach group. We saw Bach groups maybe. If we haven't, we'll see them when we see peptides. So anyway, I thought this was a pretty interesting example of what you would call they call it kinetic, dynamic, asymmetric transformations, because in essence it's driven by the kinetic product, right, which would be the lower energy intermediate, would lead to the kinetic product, right? But it's also dynamic in that intermediate can effectively, there could be two intermediates, but they will interconvert between one another. So again, I thought this was an interesting example. Yeah. Well, you would have to attack here, right?
Yeah, but that's not where it's not the mechanism for this or something like that.
Well, I didn't say, so I was just showing a potential mechanism. So I said earlier today that you could imagine either or. aryl is something like a phenyl, right? Aryl basically means phenyl. So what they actually did was they had, so this is the phenyl, they actually did some interesting chemistry where they had like a bromide appended here. And then they did some coupling chemistry where they then took this group and they actually did 1,4 type additions and built up more complexity of these molecules towards some bioactive natural product targets. So again, I think cool chemistry, and again, sort of an application of allylic alkylation that I thought was pretty neat. Okay. So moving on from one molecule that I think had applications and certainly bearings on my PhD studies to another reaction that I actually spent quite a bit of time working on when I was a graduate student. What we're going to sort of move on to now is what we call carbonyl, alkene. Alkene Metathesis. Okay, so as you guys sort of should know by this point, right? We spent some time doing Diels-Alder chemistry, and you guys know, right, that alkenes cannot undergo 2+2 additions, right? That is not allowed. If you go back to the molecular orbital theory behind this that we outlined, this wouldn't proceed, right? You'd have to use light, for example, to promote these. So it's, yeah, so you begin, when you start to get to electrons lower than, that aren't in the, if you're saying you can now invoke, say, for example, d orbitals, right? So once you can start invoking d orbitals, then that same type of process might fall apart. And I don't know as much about it once we start getting down to that level. But certainly, at least in terms of the frontier molecular orbital theory that we saw in terms of alkenes and at least sort of second row elements, carbon, nitrogen, oxygen, you can't do this, right? Furthermore, you can imagine a situation, right, where if we have colors here, we had groups here, right? I don't know how our colors are going to work out here. Purple and blue aren't the best, but I think it worked out okay. Right, when we do this rearrangement, right, you can imagine a system where, in addition to the sort of 2+2, now you've got a lot of ring strain built up in there. Certainly it can go in the reverse direction, or it could rearrange in a slightly different way, right? And form 2 new double bonds. Right, so at least in principle, in terms of paper chemistry, drawing arrows around, you could imagine a system where you could in fact do a 2+2 and retro 2+2 reaction, and you can imagine situations where that might be highly valuable, right? Say, for example, if you had a molecule such as this molecule here, right? You had a diene like this, and as you guys sort of have seen in syntheses from time to time, making, for example, rings can sometimes be challenging. But what if you could run a reaction where you could formally carry out this type of reaction, right? Do the 2+2. And then do a retro 2+2, right? You can imagine that being able to make compounds such as this one here, right, could be valuable. Right? You might also imagine that if you could do this, there could be a driving force for this reaction. Right? We've seen this time and time again, where a reaction that might otherwise be thermal, you can render irreversible, right, when the product that you generate would be a gas. Right? So we've seen this, say, for example, with nitrogen. This is just ethylene gas, right? And so you can imagine that under a system where you have a series of reversible processes that undergo this type of transformation, right, that by generating a gas, you could say, for example, take a molecule like this and perhaps make new ring systems and actually drive that by getting rid of the gas, right? So again, you could hopefully see how this could, in principle, be a valuable reaction. And so over the course of about 20 years, starting in the probably 70s, up until about the mid-90s, people were working really hard, researchers were working really hard to develop a reaction that in the 70s was sort of made as a discovery, something that would otherwise be practical. It involves metal-based catalysis. So it turns out while this reaction, for the reasons we sort of put forward, can't take place, right, based upon molecular orbital theory, explanations that we gave out previously. For the reasons that were brought up previously, if you start to invoke, say, for example, d electrons, right, or molecules that could, say, for example, have double bond character, but perhaps could have different electronic components to it, that might not necessarily have to deal with the sort of sp hybridized systems. If you have a molecule, you have a double bond, right? And you try to do the same thing, redraw this. But you did this with a metal carbon double bond. Now you have a double bond system that could have alternative, the electrons might be able to promote this process. And so this was at the beginning certainly an idea. It was first discovered again in the 70s by polymer chemists. And over time, people spent a lot of time really developing new catalytic systems that could promote this. So how would a metal, say for example, promote this? Well, metal can promote this, and it can in fact do it catalytically. So what happens is if we go back to our good old friend, the mechanism of the catalytic cycle, right, what's going to happen is that metal carbene can undergo a 2+2 with one of these alkenes now. And again, every reaction is reversible. And if you can do this metal now new 2+2 reaction, right, certainly it can be reversible. And it can go back to reform the catalyst, or it can move forward, right, in a different way to generate a new metal carbon-carbon bond, right? During this process, what we're going to generate is, say, for example, a new alkene, which we can just sort of put over here. And say, for example, that's a terminal alkene, and perhaps this might generate a gas. We'll go through some specific examples that perhaps could do this. Now, if you bring in a second equivalent of an alkene, let's say that blue one that we showed, right? Now what's going to happen is we'll be able to do that 2+2 again. And during this process, what we're going to do is now generate, say, for example, a new metal carbon bond. So in this case, what we're going to have is the metal carbon bond with the purple guy there. But again, we're still reforming that metal carbon-carbon bond. Okay. Oops. Sorry. Sorry, not to do that. Right. So in this way, what we'll be able to do is generate the alkenes that we showed earlier, perhaps making a productive bond. So this is just sort of general. So we'll get to it. So we'll talk about it in a second. We'll talk about specifically what the metals are that do this. But what we're talking about is more physically, not a ligand per se, but a metal bonded to a single carbon through a double bond. So not like a metal, so yesterday we talked a little bit about how they can bind to a metal through pi back bonding. That's two carbons though. What I'm talking about here is a metal, one carbon, double bond. Metal carbenoid. Right? So in principle, you can imagine this being a carbene, a 6-electron neutral species. We really haven't talked about carbenes that much, but this is sort of a metal carbenoid. Okay, so anyway, so this is the process. Again, when we do this here, again, I misspoke before, it's not the purple one because I have the arrows wrong, it would be the blue one, right? But nevertheless, you're now generating a new metal carbon bond, which continue to go through this process. And so certainly if you have a system like the one that I've shown over here, if you want to propose a mechanism, say for example, of ring closing metathesis, right, what can happen is, right, we can do a 2 plus 2. Retro 2 plus 2. And this reaction, if that's a CH2, right, now we're generating ethylene gas. Right, this is our metal. Now we can do a 2 plus 2 again. Right, followed by a retro 2 plus 2. Generating cyclohexene, and again regenerating that metal carbon double bond. Yeah. So that's what I was saying. It could be blue in that case. That's what I was saying. So in the current cycle, that could be blue. I was just trying to map the colors. So I can say, or metal blue. Now, if the metal blue guy were in there, right, now what's going to happen, right, is now you're going to get a metal blue guy there, and so your byproduct will specifically be the other guy. So again, you can imagine, we haven't really discussed specifically what it is, but we're just sort of mapping the electrons through the system. Here's an example where we would be generating the exact same molecule in principle, right, in terms of the CH2. CH2 over here. This is CH2 there. If we say, for example, C18 labeled this, though, right, we would get something that was a little bit. Okay, so this is a reaction called ring closing metathesis. Again, it's sort of driven, as you can imagine, by the release of ethylene gas. You can imagine certainly scenarios where this could work pretty well. One area where it actually works exceptionally well is specifically in, say, for example, medium ring synthesis. So we're pretty good at making 6-membered rings, right? Like, you guys know how to make 6-membered rings, right? How do you make a 6-membered ring really quickly? Diels-Alder, right? So certainly a Diels-Alder is a way that really powerful way. But once you start getting to larger ring systems, say 7, 8, 9, 10. A friend of mine was working on a 10-membered ring. It's not really considered, I guess, a medium-sized ring at that point. He calls it a mini macro cycle, sort of some way. But once you start getting to those bigger ring structures, it's a little bit harder to do, and metathesis has been really effective at allowing people to gain entries into those molecules much more efficiently. Yes? So what we'll discuss in turn in a second. So, because that came subsequently. So the catalyst that was developed, so I'll guys take you through sort of a historical perspective. So a lot of work had been really gone into the development of catalysts, and the metal that ended up working out really well was ruthenium, and ruthenium-based catalysts. And specifically, Bob Grubbs, in particular, at Caltech, came up with so the CY is cyclohexyl. So what he came up with, again, you look at that, it looks pretty complex, right? So he came up with this metal catalyst as what was sort of formally called sort of first generation. This isn't actually what people refer to when they talk about first generation, even though this kind of was the first generation catalyst. The one that you see used a lot more is it's the same thing, but it just changes over here. But as you can imagine, right, based upon our mechanisms, usually you can use like 1 mole percent, so one molecule of this can do like 100 reactions, sometimes like 5 mole percent, so one molecule can carry out 20 reactions. But after that first cycle, right, you can imagine that it's this phenyl group over here, methane phenyl, then you'll generate benzene, and eventually what you'll do is you'll get back to the ruthenium CH2 compound. So in all cases, this might be what you start with, but as the mechanism is sort of going on, what you formally end up having is a system where you have ruthenium CH2, right, as the active component. So you can sort of go through the mechanism on your own and see that after one cycle through, you won't necessarily generate ethylene gas over here. You might generate, say, for example, styrene, which just has a phenyl group hanging off of it. But then every subsequent process will start to generate ethylene gas. So you can sort of think about these in a way as kind of like pre-catalysts, right, that we will start with them, but after, say, for example, the first turnover, what's going to start happening is you're going to start doing other types of reactions. Now, one of the issues with this is that once you get to a molecule like this, right, when you're dealing with catalysis, you have single, especially metals, that can do lots of things, right? And so within the realm of catalysis, sometimes you can run into issues specifically associated with, say, for example, changes in the metal, right? So if the metal becomes, say, for example, modified, right, that new modification to the metal might start causing issues, right? And so the group that I was in, the Snapper group, our Snappers group did a lot of nice work on metathesis work. And he had molecules that would, say, for example, have an oxygen here, right? And so in principle, the products that you would imagine could be something like this. This gets back to sort of when certain catalysts might be useful and when other catalysts weren't. Sometimes when you would have to push this reaction really hard, like, say, for example, if there was some substituent on there, maybe not this might not be the best example, but if you had something that might slow down the reaction, you might need to heat the reaction a little bit. And what would often happen in those cases is that you would end up seeing products, say, for example, like this, where the alkene would migrate. Again, this wouldn't be through metathesis per se, but it would be through a reaction we haven't really discussed, but it's just called olefin isomerization. Again, not that important for you guys, but just to sort of recognize historically where issues arose. And a lot of it had to do early on with the fact that the first step, PCY3, sorry, I completely botched these. My advisor would have an aneurysm. So it's phosphorus with 3 cyclohexanes. So it's like triphenylphosphine, but it's tricyclohexylphosphine. Okay? All right, so sorry, my bad. So this was the thing. All right, so now that's what the PCY3 is. I'm going to erase it to save space. Now, the first reaction, so when you have this molecule coordinating, the first thing that has to happen in this reaction, right, is you need to get the other alkene nearby. And again, getting into organometallic chemistry, the first step that would have to take place is that phosphine would have to sort of dissociate from the metal. to provide some space where now the new alkene could come in, right? And so what you can do, and I'll sort of drop some of the other things here, but you create an open site here, down here, right? PCY3. And now the new alkene can sometimes come in. You have this open site down there, the new alkene can come in. Bind, say, for example, like we saw previously, right? And then go through that 2+2 retro 2+2 process, eventually getting back to the point. The important point here, though, is that when that phosphine dissociates, what kind of molecule is a phosphine? You really haven't seen phosphines that much except in Wittig olefination, and the only time you've really seen 3 phosphines was when? When we had to make the Wittig, right? And how did it serve? As a nucleophile, right? So phosphines can behave as nucleophiles, and specifically when you get to these intermediates that are less shielded, such as the one that I've shown you here. Again, the ruthenium's at a certain lowered oxidation state. And so what can sometimes happen is that the phosphine can actually add in to that carbon and set off a series of decomposition. It's a little bit more complicated, but it adds in, and then all these other things happen, and you begin to get things like this. So to get to this sort of question that Hannah was asking, there are issues, say, for example, if you want to make this reaction and push it and force it to be more active. And much of it has to do with, say, for example, the phosphine ligand. So at least towards the beginning, I would say in, say, for example, the mid-90s, people had catalysts, this sort of first-generation catalyst here, right? People had this. And they were able to do ring-closing metathesis, and it was making all these huge advances. And people started asking the question, well, if you can do it intramolecularly, could we do it intermolecularly? Because certainly coupling reactions could be very valuable, say, for example, to make alkenes. But the problem with that, right, is that once you start to take 2 components that are separate and you want them to react with one another, right, it takes a lot more energy, right, because those 2 molecules are going to need to find each other in solution. Right, there are certainly advantages energetically to having a molecule where they can just come close proximity and then react. But the cross metathesis wasn't really working that well for this, so people couldn't get the cross metathesis, what we would call, to work. And there was really 2 advancements that were made. Well, there's lots of advancements that continue to be made, but perhaps 2 of the big advancements, particularly as related to cross metathesis. Okay, and so what we're talking about for alkene cross metathesis. Right, so what we're talking about is a system where you have, say, for example, 2 alkenes, R1, R2, and they react, and you get, say, for example, a new alkene like this. Right. And so one of the ways that people took this catalyst and actually made it more active was to add a new ligand to it, a non-phosphine ligand, which on the one hand you could imagine would at least quell a little bit that sort of phosphine dissociation decomposition, but also had some other more technical effects in terms of these things that people call like cone angles, and basically just changing the geometry and putting it into a more active form. And this catalyst came to be known as the 2nd generation drugs catalyst. The ligand is kind of interesting. It's called a arduino carbene, so it's pretty complex. You have these mesotelial groups on there. And I'll just show this like that for the time being. But it was effectively the same catalyst, but it had this carbene up here. So again, that's a carbene. Again, it's a 6-electron species. It's sometimes a little bit difficult to draw the carbene bonded, but usually the way that people will draw it is like this. That's how historically people drew it, but that kind of suggests that there's a hydrogen there, which there's not. So really probably the best way to draw it would be something like that. Again, important point is this is second generation Grubbs catalyst. And I would say that was probably the second advancement, at least in terms of ruthenium catalyst. The third advancement actually took place while I was at Boston College by one of the faculty members at Boston College. And what they found, actually based upon some discoveries that were made in the snapper group that I was in, were that there were active catalysts that could actually get rid of this phosphine altogether. And so there's a paper, it was kind of neatly called a sort of caught in the act catalyst, because what they found was that they could make these catalysts that actually didn't have any phosphine in them at all. And just sort of really quickly, I'll just kind of show you, it's not going to be the exact, but it'll at least give the flavor of what they sort of found, was if you had molecules such as this molecule here, and you treat it with, say, for example, ruthenium metathesis catalyst, what would happen is you would get molecules whereby the ruthenium was actually coordinating to now an alkene, right? And so this was a molecule that they took and they isolated it and then they resubjected it and found that it still had the activity. So it was kind of an intermediate, right? That was the intermediate of say, for example, the ring opening, or that's one thing we studied, or like we saw ring closing, right? If you think about the reverse. And so you're able to basically bind in the sphere and have additional things. So down the hall, Amir Haveda was working in similar types of situations related to the metathesis catalyst. And what they found is that you could actually get rid completely of the metathesis catalyst by simply putting a nice epoxy group down here. And I'll just abbreviate this in H2IMES. But now that oxygen there will actually bind where the sort of phosphorus normally bound. And they did some really nice work with this catalyst. Now you've got a molecule that doesn't have any phosphine in it at all. It's much more thermally stable, so you can heat this reaction up much, much higher and not get some of those decomp products that I suggested earlier. And again, with these types of catalysts, now you can do sort of cross metathesis. H2IMES is just this. It's just the abbreviation for this. Okay, so it's the same thing. It's called H2, like imidazole, 2 hydrogens on imidazole with mesothyl groups. So. Anyways, I'm not going to ask you to draw the metathesis catalyst. But the more important thing is selectivity in cross metathesis, right? Certainly if you take ring closing metathesis, I think it's a little bit easier to say, okay, if I'm going to make a ring, I can make a ring, right? But if I want to do cross metathesis, you can imagine the entire process is reversible, right? So if you have a system where you have R1 plus R2, and you treat this with, say, for example, one of these catalysts, what's going to end up happening in principle, right, is that in addition to system trans, you can just assume that it's going to be trans, right? I told you that the system's reversible, so you can assume the thermodynamic product. But in addition to getting the sort of the coupling product, what you can also imagine getting is dimers of this and this, right? So you can imagine systems where you've got R1 and R1, R2 and R2. So these would be dimers. Right? And so you can imagine that from a practicality standpoint, sometimes cross metathesis might not be all that useful. Now, you can imagine some sort of tricks that you might be able to play if, say, for example, these are the same, right, type of molecule, roughly. If you wanted to maximize your yield of this, and say, for example, one of these was precious, you could just use, say, for example, a large excess of the other one, right? And sort of drive it based upon stoichiometry. So if you have a lot of this, you'll limit this You'll still get a lot of this, but at least you'll maximize, say, for example, R1. So you can certainly play with stoichiometry. That might be one way you can do it. But it turns out that the reactions are pretty selective if you have the appropriate electronics in these systems. And what I mean by that is if you have one alkene that is, say, for example, electronically poor alkene, it will react really nicely with sort of more electronically neutral alkenes. So chemistry that works really well with these molecules is, say, for example, if you take ethyl acrylate, right, which is electronically poor, as you might imagine, because of the carbonyl there, right, and you treated that with, say, for example, styrene, right, which is more of an electronically rich alkene, or say, for example, even aliphatic alkene. What I mean by that is, say, for example, just an alkyl chain here. Those wouldn't necessarily be electronically, these would be sort of matched in a way, right? And so you have an electronically poor one. And in these cases, the reaction works really, really well. And I think this was molecules like the one that I showed you there. And so this would work great. Like I think usually you might add like, instead of having to add like a ton, like whichever one's your precious one, you might just have to add like 2 equivalents. You don't have to be like 20 equivalents or something like that, but you just have to add a little bit of excess, and you can get basically quantitative yields of this reaction. So it can work really, really well in that chemistry. The reason why this does this, I mean, we can discuss, but it more has to do with the fact that the metathesis reaction works the fastest on more electronically rich or neutral ones. It'll go on there the fastest. It's the slowest to go on electronically poor ones. But the thing is that once you generate this guy over here, this electronically poor alkylidine over here, it will react very, very quickly with one of these. So it goes on to this first. Again, if you show a mechanism, you go this way. I'm not going to penalize you, but I'm just trying to explain. It will go on this one the fastest. Or sorry, not fastest. It'll go on this one slower, but once it gets on this, this is the most reactive alkylidine, which will then immediately react with the other alkene solution. So it basically plays with the fact that it goes on this one faster, but again, in a solution, it can go on, it can come off, it can go on, it can come off. The moment it goes on to this one, it's going to be much more reactive, so it's more prone to, say, for example, find one of these react, and then you get the product. So that's just the sort of idea there. So again, cross-metathesis is a really useful process. It also extends to alkynes. So this is kind of, I think, an interesting mechanism to sort of discuss. So we learned ring-closing metathesis, right? And we learned cross-metathesis. This is just chemistry with double bonds, right? And so if you're just doing a 2+2, retro 2+2, you can imagine a lot of similar types of chemistry taking place on, say, for example, alkynes. And the question that could arise in those cases is, well, what might the product be if you did it on alkyne? And so this is called E9 metathesis. Okay. So instead of having a molecule like instead of having a molecule like a diene, what if you had an alkene and an alkyne, right? What might the product be that would form through this reaction? Now, the first question might be, well, which one of these might the ruthenium react with first? It's sort of, in a way, doesn't really matter that much, but because you can sort of get to the products either way, but you can imagine, and there's actually a problem that I give in one of my practice exams, or in my practice problem sections that kind of deals with how where you start can lead to different types of products within the United Metathesis. But in general, I think it would just be best to start with the alkene, right? That's probably the easiest one to put on there first. I think based upon the 2+2 retro 2+2 argument, right, you could get to that species here. Right, so you just go to ruthenium 2+2, retro 2+2. you're now going to have the ruthenium carbon double bond. And now let's see what happens, right? If we take this ruthenium alkylamine and we, again, try the 2+2 retro 2+2 process, what would form? Well, let's start, right? So if we start with the 2+2, what we're going to generate now is cyclobutane again, but now it's going to be a cyclobutene, right? It's going to be a metallocyclobutene, right? Because that alkene, that alkyne, that's only one of the pi bonds that's going to react. It's going to leave behind another pi bond, right? And then if you do a 2+2 again with this, what's going to happen is you're going to generate a new ruthenium alkylamine, okay? So what does this start to look like? It kind of starts to look like a diamine, right, in a way. And so you can imagine, right, in this case, at least as I've drawn here, that first reaction, if we treated this with the ruthenium alkylamine, right, the product that we would generate through that first process of the ethylene. And so now you can imagine a mechanism where, say, for example, the ethylene would come back in, do the 2+2 retro 2+2. Is the ethylene still in solution? And now you can start to get to molecules like dianes, right, in a catalytic way. You can also imagine if we did this reaction in the presence of another alkene, what might happen, right? We might actually now get, let's say, for example, this was in the presence of an R1. Now we might actually get molecules like this, right? To go from some simple starting materials and make tons of carbon-carbon bonds in a single event. So this one that I just showed here, what do you think it would be called? It would be an E9 cross metathesis, right? Because it does the E9 metathesis followed by a cross metathesis. And so one of the really cool developments in metathesis have been sort of cascade processes like this, where if you understand the mechanism, I think it's a fairly simple mechanism, right? That's one of the reasons why I like to teach this one, because I think it's a good one to sort of think about moving electrons. You do 2+2, you do retro 2+2, you count, make sure everything is where it needs to be. And you guys could probably start to imagine, even on your own, types of reactions and types of cascade processes that might use this reaction fairly effectively to build up a lot of complexity. And so this sort of area of cascades, metathesis cascades, has been pretty big. Yes? So, well, let's see what can happen. So, there was a lot of studies, guys, Buffalo Stephen Diver did a lot of work on mechanisms related to this. And all I remember is it was E and I, and kind of had E9 metathesis. I don't remember the reasons why. But if you think about the fact that this reaction leads selectively to products like this, that might seem rational, right? You're forming a 6-membered ring. But what about a situation where you say, for example, form a 5-membered ring? Right? Right. In this case, now you're getting a 5-membered ring, and I'll explain what I'm talking about in a second. Right? You get that one. If you did the alkyne first, right? The ruthenium could go one of two ways, right? And you can imagine a system where we get that alkylidine, right, as well as this alkylidine there. So if the ruthenium goes So if the ruthenium goes to this carbon, you're going to get the molecule where the ruthenium's on the same bond as the R group. If it goes the other direction, you're going to get the opposite, right? So if you do the 2+2 here, followed by retro 2+2. Now you're going to get that molecule there, right? And now if you have these two metal alkylamines, this one would in principle lead to the product, but this molecule would lead to what? A 6-member ring, right? And you never see that one, right? So unless you somehow try to sort of try to rig the system so it works that way. So you almost never see this product here. You only see this product here. And if you imagine it would go after the alkyne, that might suggest that you would get a mixture of both of those products. And so once you put the ruthenium on here, you got to go that way, because otherwise you'd be like twisting the molecule, right? Does that make sense? Yeah. So anyway, so that's hopefully explain that a little bit. One other reaction, so we've got about a little over 10 minutes left. There's been some other kind of neat advancements. One of the reactions, again, sort of since I'm new to this stuff, I sort of alluded to this. I alluded to this earlier when I was talking about my PI's work. But you can certainly do ring closing metathesis. Ring opening metathesis can also take place, right? So especially if you have, say, for example, strained molecules, right? So if you have a 6-member ring, it's not going to want to open. But if you have something like a strained molecule, such as the one that you see here, and my graduate advisor worked on a lot of molecules that looked like this. We'll try to use them to generate larger ring systems. And one of the things that he sort of did early on that was really neat is he would take molecules like this, right? He would then take these molecules and treat them with, say, for example, metathesis catalysts. And he would get the molecules like this. And what do you think would happen with molecules like this when you heat them up? They would do Cope rearrangements, right? And we get the medium-sized rings like that 8-membered ring there. So again, he found quite a bit of value early in his career in ring opening conditions. The one issue with ring opening metathesis, though, is so he found that it actually works pretty well, and they found a lot of uses to it, specifically in examples like this. Some really nice synthesis work in this regard. But the issue is you need to make sure that you do a cross metathesis. So it's very difficult to just do, say, for example, ring opening metathesis. You need some type of alkene in there, right? And the reason is that this is going to be highly reactive. It's highly strained, so catalysts will react with it really quickly. And the problem is if a metathesis catalyst reacts with it really quickly, what's going to happen is you're going to end up generating molecules, new alkylamines, right? And if you don't have some other alkene already on there, what's this probably going to have to react with? This, right? And then you're going to generate a new one, which is going to react with that. And then what's going to happen? A big polymer, right? And so metathesis actually had a lot of roots in polymer chemistry. So people like this. This was called sort of raw ring open metathesis polymerization. And if you ever see for whatever reason, if you see a Bob Grubbs talk, they'll often have a polymer on hand that's got like a bullet lodged in it, because he basically made this polymer and shot it with a bullet, and it stopped the bullet. I don't know, it's just sort of one of those wild things. So anyway, so you can see there are examples of ring open metathesis, but generally what you need is some type of cross partner in there. Generally so that ruthenium can go on there first, right? And that's just going to likely sort of impede it. It's going to intercept this so that it doesn't react with itself, and so on and so forth. And so generally it's ring open cross metathesis. Another development that I thought was kind of neat when I was in grad school, again, deals with asymmetric catalysis, right? This sort of idea of generating stereogenic centers, for example, using catalysts. And I thought this was kind of creative in a way. And that's, you look at the chemistry that we're sort of doing here, and by and large, we're making carbon-carbon double bonds. And carbon-carbon double bonds, by virtue of the fact that it's an sp2 hybridized center, doesn't inherently have chirality. to it, right? You're not generating chirality, right? If you did, we showed the example previously where there was a stereogenic center with a palladium catalyst, and so you can imagine that forming. In the case of metathesis, though, it becomes a little bit trickier. You need molecules that are inherently achiral, but if you were to, say, for example, react them with some chiral source, it would become chiral. And an interesting example of that you could imagine would be this one here, right? Like, so you have these molecules. If you had a molecule that was, say, for example, if we say, for example, drew in the stereochemistry here, and let's say, for example, you did a ring opening, right? You could imagine that the product that I showed over there wouldn't matter. So this molecule is not chiral either. What is that molecule considered? I mean, these are chiral centers. These are stereogenic centers as well, right? But the molecule is not chiral. Why? Meso, right? The same thing over here. It's meso. But if you can desymmetrize that, say, for example, by selectively reacting with one of these, you desymmetrize that, right? And you take those two chiral centers, and by desymmetrizing the molecule, you now generate chirality over a molecule. So you basically take the stereogenic centers, desymmetrize the molecule, and you can do asymmetric catalysis. And so, I don't know if they've done it with this type of substrate, but they've done it with more strained cyclo molecules like this, where you have cyclopropene, right? If you have like groups up here, this is also work that friends of mine did at Boston College. And again, they were able to use chiral catalysts to get stereochemical control. And again, I can't draw those up on the board like I did some of the others. I don't remember them all that well. But in general, maybe I could. You can imagine they're all based on that initial discovery. But usually what would happen is there's a whole variety of classes to them. But some of them, I believe, would have like, I forget, I think they had like things like this, where you can imagine, I'm sort of making this up, I think it was something like this, where you can imagine that if you had this sort of torque to it, right, it might lock it in a specific position, but what they would also need to do is have chirality up here that would force it to be in a certain, anyway, it doesn't really matter. But they're having these chiral catalysts. So, anyway, I mean, that's, I think, probably it for the metathesis reaction. Does anybody have any questions? All right, so what I think I will do in the remaining time here is perhaps what we can do is I can throw up a mechanism problem using the metathesis reaction. And you guys can sort of try this. I think metathesis, you can pretty much expect a metathesis cascade question on an exam. In part because I think that they're simple mechanistically, right? 2 + 2 retro plus 2 + 2. That's all you have to know. But it's a good way to sort of practice making sure that you're keeping track of all your bonds, really strategizing and problem solving with what I would argue is fairly simple. Yeah. This? I was just making up a chiral catalyst. They made catalysts that had feeling something like this, and it's chiral, right, at ruthenium, right? And so if this leaves, right, the metal can't really come from this face because, say, for example, it's blocked from stuff here, so it can only come from the other face, generating new chiral molecules. So I was just sort of showing that there's some interesting uses of that. All right, so. Okay, I'll show an example of an idea that a friend of mine had that he was working on when he was a grad student that involved sort of relay catalysis. So the molecule that he was working on, that molecule is called like this. I forget exactly the idea here. But what he was trying to do was he was trying to relay the chirality over here to basically do a single ring opening product. Okay, so yeah, so this was the reaction. Okay, catalyzed by ruthenium catalyst. So why don't you guys go ahead and give that a shot? Think about how that reaction might take place. So it's a relay process. What he's trying to do is he's trying to promote a ring opening metathesis reaction. Okay, and effectively get only a single. This kind of goes back to what we were talking about before, of trying to make sure that it reacts with a single alkene of the other one, but this needs to be by delivery. Give that a shot. I see pencils to paper in about half the and arrows at his laptop. His laptop. And see you got it, I'll bring up the board. Well, write it down. Oh yeah, that's fine. I'll just put it. It's not important. And again, the other advantage to a method like this, right, would be that you're generating a double bond that sits together. And so somebody showed me a mechanism that looked great, and fine, but it didn't explain the selectivity. Well, I guess it doesn't really matter at that point. I don't know that it could. I'm trying to think how what selectivity I should be talking about. Because I guess the only other selectivity would be if this somehow reacted over there. And that's probably not going to happen anyway because it's two strands. So let's go ahead. Put that up there. I think actually now I'm thinking about your something fine. Chalk these down to the. Sorry, I don't have much to talk about. So right here. So I think there's a couple options here, and I think what I was thinking initially was perhaps that it would react with the terminal alkene. The question is, do you guys think that it would actually react with that first or not? And that's the sort of question I'm not really sure. You might expect it would react with the strained cycloalkene first, right? And that's what I was talking about regio selectivity, why would the ruthenium go one way rather than the other? Well, that's what I was saying earlier, right? So you're thinking about the carbenoid character to it, which is good, right? And that also explains why I said that's more reactive. So it's slower to go on, faster to react. That's remember when I was talking about the selectivity of the electronically poor one. It's going to go on there slower, but once it goes on there, it's highly reactive. But you don't need highly reactive alkene to react with such a strained double bond. So more likely it's either a mechanism such as the one that's shown here, or perhaps there's going to be some intermediates. Yeah, you're just off. Your carbon is just off. You moved your carbon. The carbon. Okay. Yeah. So and I think you added another carbon there. You had it perfect up until your very last structure. See the oxygen? You have like an extra carbon in there. Yeah. 1, 2, 3, 4. Great. Stay right now. Yeah, so this is sort of I would call this the cascade process, right? It's kind of a ring opening, ring closing process. You could imagine, like we were saying, you can imagine a mechanism whereby it would go on the terminal alkene first, right? You can imagine the ruthenium ending up here first, right? And then perhaps reacting. But I think this mechanism, I like. Yeah, I think in metathesis especially, I think, I've tried to sort of drill home this idea that every reaction, every step is reversible, and certainly that's true in the metathesis process. So, again, there are some examples there's one example in particular. It's a relay metathesis approach by this guy Tom Hoy, his research group. Cool stuff. Basically finds that if you have appended alkenes that set off metatheses reactions from one side of a molecule or another side of the molecule within relay processes or within cascade processes, you can actually get a different product. So that would be an example where there would be a case, but in this case, it doesn't really matter how the mechanism is. So, all right, with that, I'm going to call that a day. At 1 o'clock today, I need to sort of call it a day. So make sure to get to me before 1 if you want to come during office hours.